For any assignment-related queries or info, call us at +1 678 648 4277. You can mail us at info@architectureassignmenthelp.com or reach us at https://www.architectureassignmenthelp.com. Part A, Branch Prediction. Consider a fetch pipeline based on the UltraSpark 3 processor, as seen in Lecture 5. In this part, we evaluate the impact of branch prediction on the processor's performance. Assume there are no branch delay slots. Here is a table to clarify when the direction and the target of a branch/jump is known. Instruction taken known. At the end of, target known. At the end of, BEQZ/NES-RBJB, always taken, BJRB, always taken, R. ArchitectureAssignmentHelp.com. Question 1. We add a branch history table, BHT, in the fetch pipeline as shown below. The A stage of the pipeline generates the next sequential PC address, PC +4, by default, and this is used to fetch the next instruction unless the PC is redirected by a branch prediction or an actual branch execution. In the B stage, branch address calc/begin decode, a conditional branch instruction, BEQZ/BNEZ, checks the BHT, but an unconditional jump does not. If the branch is predicted to be taken, some of the instructions are flushed and the PC is redirected to the calculated branch target address. The BHT determines if the PC needs to be redirected at the end of the B stage and the new PC is inserted at the beginning of the A stage. The A stage also contains the multiplexing circuitry to select the correct PC. To improve the branch performance further, we decide to add a branch target buffer, BTB, as well. Here is a description of the operation of the BTB. 1. The BTB holds entry_PC, target_PC pairs for jumps in branches predicted to be taken. Assume that the target_PC predicted by the BTB is always correct for this question. Yet the direction still might be wrong. 2. The BTB is checked every cycle. If there is a match for the current fetch PC, the PC is redirected to the target_PC predicted by the BTB, unless PC is redirected by an older instruction. The BTB determines if the PC needs to be redirected at the end of the P stage and the new PC is inserted at the beginning of the A stage. ArchitectureAssignmentHelp.com. For a particular branch, if the BHT predicts taken and the BTB did not make a prediction, the BHT will redirect the PC. If the BHT predicts not taken, it does not redirect the PC. A. Fill out the following table of the number of pipeline bubbles, only for conditional branches. ArchitectureAssignmentHelp.com. For both Part B and Part C, below, assume the BTB contains few entries and is fully associative, and the BHT contains many entries and is direct mapped. B. For the case where the BHT predicts not taken and the BTB predicts taken, why is it more probable that the BTB made a more accurate prediction than the BHT? Since the BTB stores the PC, we are certain that the BTB entry corresponds to that particular branch. Also, because the BTB is much smaller than the BHT, when there is a BTB hit, it is likely to be for a branch that was recently taken. The BHT is direct mapped and untagged, and it is possible that there may have been conflicts, so the entry in the BHT may not actually belong to this particular branch. Therefore, in this case, the BTB is more likely to make a better prediction. C. For the case where the BHT predicts taken and the BTB predicts not taken, why is it more probable that the BHT made a more accurate prediction than the BTB? If a branch is not found in the BTB, it could mean either of two things. 1. The branch was predicted not taken, or 2. The branch was predicted taken but it was kicked out of the BTB. Since the BTB has few entries, it is likely that the branch could have been kicked out of the BTB. Since the BHT has more entries, it is likely that the branch is still in the BHT, so the BHT will probably make a better prediction than the BTB in this case. ArchitectureAssignmentHelp.com. Question 2. We will be examining the behavior of the branch prediction pipeline for the following program. Given a snapshot of the BTB and the BHT states on entry to the loop, fill in the timing diagram of one iteration, plus 2 instructions, on the next page. Don't worry about the stages beyond the E stage. We assume the following for this question. 1. The initial values of R5 and R1 are 0, so BR1 is always taken. 2. We disregard any possible structural hazards. There are no pipeline bubbles, except for those created by branches. 3. We fetch only one instruction per cycle. 4. We use a 2-bit predictor whose state diagram is shown below. In state 1x we will guess not taken, in state 0x we will guess taken. BR1 and BR2 do not conflict in the BHT. ArchitectureAssignmentHelp.com. 5. We use a 2-entry fully associative BTB with the LRU replacement policy. ArchitectureAssignmentHelp.com. Question 3. What will be the BTB and BHT states right after the 6 instructions in question 2 have updated the branch predictor's states? Fill in 1. The BTB and 2. The entries corresponding to BR1 and BR2 in the BHT. Part B. Cache Performance Analysis. The following MIPS code loop adds the vectors x, y, and z and stores the result in vector w. All vectors are of length n and contain words of 4 bytes each. W, I equals x, I plus y, I plus z, I for 0 equals I less than n. ArchitectureAssignmentHelp.com. Registers 1 through 5 are initialized with the following values. R1 holds the address of x, R2 holds the address of y, R3 holds the address of z, R4 holds the address of w, R5 holds n. All vector addresses are word-aligned. The MIPS code for our function is loop LWR6, 0, R1, load x. LWR7, 0, R2, load y. LWR8, 0, R3, load z. Add R9, R6, R7, do the add R9, R9, R8 SWR9, 0, R4, store w. Add R1, R1, 4, increment the vector indices. Add R2, R2, 4, 4 bytes per word. Add R3, R3, 4. Add R4, R4, 4. Add R5, R5, -1. Decrement n nes R5, loop. ArchitectureAssignmentHelp.com. We run the loop using a cache simulator that reports the average memory access time for a range of cache configurations. In Figure B1, on the next page, we plot the results of one set of experiments. For these simulations, we used a single-level cache of fixed capacity and varied the block size. We used large values of n to ensure the loop settled into a steady state. For each block size, we plot the average memory access time, i.e., the average time in cycles required to access each data memory operand, cache hit time plus memory access time. Assume that capacity, C, and block size, B, are restricted to powers of 2 and measured in 4-byte words. The cache is fully associative and uses an LRU replacement policy. Assume the processor stalls during a cache miss and that the cache miss penalty is independent of the block size. ArchitectureAssignmentHelp.com. ArchitectureAssignmentHelp.com. Question 4a. Based on the results in Figure B1, what is the cache capacity C? When C less than 4b, there are less than 4 lines in the cache, so all 4 vectors,